My name is Joseph Zuckerman from Columbia University, and on behalf of my co-authors, Davide, Jihye, Paolo, and Luca, I'll be presenting our work Cohmeleon, learning-based orchestration of accelerator coherence in heterogeneous SoCs. Modern SoCs contain an increasing number of hardware accelerators, and many are designed with a loosely coupled approach, in which they lie outside of the processor core on the system interconnect and execute coarse-grained tasks when invoked with a device driver. In particular, we focus this work on fixed-function, loosely coupled accelerators, which are not programmable, but can be highly configurable. The literature shows a variety of ways in which loosely coupled accelerators interact with the memory hierarchy of SoCs. We categorize the existing literature into four main methods based on the degree to which they leverage one or more levels of the cache hierarchy. We refer to these methods as cache coherence modes. In some of these modes, coherence is enforced purely in hardware, such as the fully coherent mode, where the accelerator has its own private cache and participates in the system's coherence protocol, just like processor cores. The coherent DMA mode is similarly enforced in hardware, but without an accelerator private cache. Other modes require the involvement of software to maintain coherence. In the non-coherent DMA mode, the accelerator accesses off-chip memory directly. The LLC coherent DMA mode lies in the middle of this spectrum, with the accelerator performing DMA to the last level cache. Each of these modes has a set of trade-offs in terms of the cache flushes required, the overhead of each transaction, the size of data transfers, and more. Furthermore, most solutions choose a fixed coherence mode per accelerator or the entire SoC at design time. As motivation for Cohmeleon, we perform a set of experiments with 12 accelerators on FPGA, including the open source NVIDIA Deep Learning Accelerator. We run each accelerator in isolation with 3 different workload sizes for each coherence mode and report the execution time, shown in green, and the off-chip memory accesses, shown in yellow. Lower bars indicate faster execution time and fewer off-chip memory accesses. There is clearly great diversity in these results, but I'll highlight a few important trends. For a particular accelerator, the best performing mode can vary based on the workload size, as is shown for the sort accelerator, where the coherent DMA and non-coherent DMA modes perform the best for small and large workloads, respectively. For a particular workload size, the best mode can vary depending on the accelerator, as shown by the Cholesky and GEM accelerators with large workloads, where the non-coherent DMA and LLC coherent DMA modes perform the best, respectively. Finally, an incorrect selection of coherence mode can be detrimental to performance, as highlighted by an 8x slowdown for the autoencoder accelerator with full coherence. These workloads show that there is no clear winner for any accelerator or workload size, and that SoCs, and even particular accelerators, have heterogeneous coherence needs. As further motivation, we run additional experiments with multiple accelerators running in parallel using the same coherence mode and report the performance compared to the accelerators running in isolation. It is clear that each coherence mode suffers a different performance degradation, with the non-coherent DMA mode degrading the least. This shows us that performance of coherence modes can be impacted by contention on shared resources, or more generally, by the dynamic status of the SoC. Thus, we propose that SoCs should support multiple coherence modes for accelerators and the seamless selection from them at runtime. However, it's infeasible to expect application developers to manage this decision. There's an enormous state space of variables that can affect the optimal choice. Some attributes are static, like the architectural parameters of the SoC, such as cache sizes, channels to memory, the coherence protocol in use, and the type of system interconnect. Others can change dynamically as workloads and utilization patterns change, and accelerators are configured with different parameters. It's unclear how all these variables can impact performance without performing an exhaustive search, and it's unrealistic to expect application developers to understand all of these variables or know under what conditions their apps will be run. Thus, we make the case for a learning-based approach that can automatically discover best coherence mode decisions. We identify 3 main characteristics for an appropriate learning approach. First, it should train online during normal SoC operation. Next, it should require no prior knowledge of the SoC architecture nor any training data. Finally, it should be able to continuously update itself as new workloads and states are encountered. These requirements led us to use reinforcement learning, in which an autonomous agent learns behaviors through trial and error interactions with the environment. In particular, we select Q-learning, a type of reinforcement learning that maintains a Q table of Q values for state action pairs. Q values are updated using the reward received by taking a particular action from that state. Q-learning can optimize for a desired objective by defining an appropriate reward function. In Cohmeleon, we define the Q-learning model using states that are the status of the SoC, such as number of accelerators running, the size of workloads, and the coherence modes in use. The actions are the available accelerator coherence modes, and the reward function is defined as a weighted combination of execution time and off-chip memory accesses. We built Cohmeleon on top of ESP, our open source research platform for agile SoC design. ESP is a natural starting point for one possible implementation of Cohmeleon, as it offers runtime selection of coherence modes for accelerators. Furthermore, ESP provides push-button generation of FPGA prototypes, which allowed for experimenting with many different SoCs. The ESP architecture is built on top of a 2D mesh multi-plane network on chip. There are 4 types of tiles: processor tiles, accelerator tiles, memory tiles, and the auxiliary tile. Each tile contains a socket that implements platform services like coherence, performance monitors, DMA, and interrupts. Building Cohmeleon required several changes to ESP. First, we augment the ESP API for accelerator invocation, which runs on Leon 3 processor cores in this work, to keep track of variables like the number of active accelerators, their workload sizes, and the coherence modes in use. A reinforcement learning module is also implemented in the ESP API and runs transparently to application developers. We also implemented a hardware monitoring system in ESP for accessing performance counters from software running on the FPGA. We measure the accelerator cycles and off-chip memory accesses to evaluate the quality of an accelerator invocation. The hardware monitoring system adds negligible area overhead to the SoC. As shown in the figure on the right, one iteration of Cohmeleon starts with software determining the status of the system and performing a lookup in the Q table to the corresponding state. Then, when optimizing for performance, Cohmeleon will select the action with the highest Q value and write that coherence mode to the coherence configuration register of the accelerator tile. The accelerator will then run, and when complete, Cohmeleon reads the performance monitors and uses this information to update the selected Q value. We choose to configure the accelerator's coherence once per invocation to avoid excessive overhead associated with switching coherence modes. ESP provides several design flows for accelerators with automatic SoC integration. These design flows operate at various levels of abstraction, including RTL, high-level synthesis from C, C++, or System C, and directly from high-level machine learning models using the open-source HLS4ML tool. ESP also provides flows for integrating third-party accelerators that comply with standard interfaces. These accelerators can then be seamlessly combined with other types of tiles from the ESP SoC configuration GUI. We use several accelerators available in ESP to design 7 different many-accelerator SoCs for FPGA. 4 of these SoCs are based on a highly configurable traffic generator that allowed us to study a wide range of communication properties with the effort of only one design. 3 SoCs use real accelerators. 1 contains 10 of the accelerators from the motivation section. 1 targets the autonomous driving domain with FFT and Viterbi accelerators for vehicle-to-vehicle communication, and matrix multiply and convolution accelerators for CNN execution. A final SoC targets the computer vision domain with night vision, multi-layer perceptron, and autoencoder accelerators. All of these accelerators are available open source in ESP. We also developed a multi-threaded application for each SoC to invoke accelerators in a diverse set of ways. The application is organized in phases that vary in terms of the number of accelerators operating in parallel and the workload sizes that are used. We evaluate Cohmeleon in comparison to several baselines, including design time and runtime decisions. For design time, we use a fixed homogeneous decision that applies a single coherence mode to the entire SoC. The fixed heterogeneous decision applies a single coherence mode to each accelerator based on a design time profiling. For runtime decisions, we include a random policy to show the performance of runtime selection without intelligence. We also use a manually tuned algorithm, which is a heuristic that incorporates information about the status of the SoC that we developed by collecting extensive data from tens of thousands of accelerator invocations. The fixed heterogeneous and manually tuned algorithm represent state-of-the-art solutions. This first set of results highlights the performance from 4 different phases of our test application on one of the traffic generator SoCs. The phases vary in terms of the number of accelerators working in parallel and the workload sizes used. Each phase shows a different relative ordering of the fixed homogeneous modes, which are the first 4 on the left of each plot. This further emphasizes the need for runtime coherence selection, as there is again no single winner across these phases. In contrast, Cohmeleon and the manually tuned algorithm both match the best performing coherence mode in each phase. Cohmeleon has an execution time similar or better than that of the manually tuned algorithm, while improving on off-chip memory accesses in all phases due to its multi-objective reward function. This next graph shows the average performance for each method across all phases of the evaluation application, with execution time on the x-axis and off-chip memory accesses on the y-axis. The closer a data point is to the origin, the better its performance is. We can see significant variation in the performance of the fixed homogeneous modes. We can also see that the fixed heterogeneous mode does not show improvements over all of the fixed homogeneous modes. We show several results for Cohmeleon, where each data point uses a different reward function, obtained by changing the relative weighting for each objective. Cohmeleon and the manually tuned algorithm achieve Pareto optimal results. Cohmeleon achieves close to the best execution time, while also achieving the minimal off-chip memory accesses. Furthermore, there is not significant variation among most of the different reward functions, implying that minimal tuning is needed. Next, we show the breakdown of coherence mode decisions for Cohmeleon and the manually tuned algorithm across all invocations and also broken down by workload size. We can see that Cohmeleon learns a form that is roughly similar to the manually tuned algorithm. However, in all cases except for extra large workloads, Cohmeleon relies less on non-coherent DMA and more on the coherent DMA and LLC coherent DMA modes. The non-coherent DMA mode typically has the most off-chip memory accesses for workloads that fit in the caches, so Cohmeleon tries to avoid this selection due to its bi-objective reward function. However, as seen on previous slides, it does this without sacrificing performance. We also examined the impact of training time on Cohmeleon. In this experiment, we alternated one iteration of the training application with testing on a different application and recorded how the performance changed over time. We repeated this process for 10, 30, and 50 iterations of our application, which contains roughly 300 invocations. We can see a quick drop off in the performance after just one iteration from an untrained model. Thereafter, there is some oscillation in performance as the model continues to explore different states, but the model ultimately converges. After 10, 30, and 50 training iterations, Cohmeleon achieves roughly the same performance. So we can see that Cohmeleon can be trained relatively quickly, and the number of training iterations doesn't have a significant impact on final performance. We report the execution time overhead incurred by Cohmeleon as a percentage of the total accelerator invocation time for 4 real accelerators. This overhead is included in all prior results. For small and medium workloads, the overhead is just a few percentage points. For large workloads, which tend to be more common, the overhead is negligible when compared to the invocation time. The overhead is small because Q-learning requires only a handful of arithmetic operations for each iteration. Finally, we look at the results across all SoCs, and we can see that the trends hold. Cohmeleon generalizes to different SoCs and achieves a Pareto optimal performance on all. The manually tuned algorithm does not always generalize as well. For instance, on SoC5, its performance is Pareto dominated by Cohmeleon. Across all SoCs, Cohmeleon achieves an average speedup of 38% with a 66% reduction in off-chip memory accesses when compared to the design time solutions. In conclusion, we saw that accelerator performance can vary greatly by merely changing the coherence mode used. We propose that SoCs should support runtime selection of multiple coherence modes for optimal performance. Reinforcement learning can be used to manage this selection by automatically discovering optimal decisions. Cohmeleon provides significant performance benefits on multiple objectives while adding negligible area to the SoC and minimal overhead to the accelerator invocation. We released Cohmeleon as a part of the open source ESP project and successfully completed micro artifact evaluation. Thank you for listening, and we hope you'll join us at our live talk at session 4A of Micro 2021 on Tuesday, October 19th at 3:15 p.m. Eastern Time.